Good afternoon to everybody who managed to join Sano Seminar. Today we are very happy to host Mateusz Pieniak. Mateusz is a senior applied NLP scientist at the company Evidence Prime. And Mateusz agreed to present the ideas which are related with text classification. But while the word text is not present in the title, but it will be a talk will be in large part about text classification, which is very important in our practical medical application. So, Mateusz, the floor is yours.
So, hello, everybody. As Marian said, we'll discuss classification for text, but a specific variant of classification called Imbalanced one. And I will share the lessons we learned during tackling this problem for a specific medical domain, which is for scientific literature and especially for systematic reviews. So my name is Mateusz and I work as a scientist for Evidence Prime. We are the remote first company located in Krakow, and we are a spin-off from University of McMaster in Canada, which is sort of a Silicon Valley of something called evidence-based medicine. Currently, we have 20 people on board with 8 software engineers who create different tools. And these tools are for WHO, European Commission, different government agencies, some medical societies, and pharmaceutical companies. I have 2 case studies I will discuss today for that we managed to accomplish with collaboration with our clients. So before we start, you've seen the systematic review in the title of the presentation, so I will briefly explain what systematic review is. So systematic review is basically an aggregation of different studies, but this is an unbiased aggregation. So if you want to answer a specific question, then we need to have a very comprehensive search over the available studies and then select the study that fits our criteria. And this is like an example because usually systematic review ends up with something called meta-analysis as the forest plot. So as the rows in this table, this table represents the systematic reviews that tries to answer the question whether adding corticosteroids, this is some sort of inflammatory drug, to a standard care, which is like being in a hospital, whether it increases or decreases the mortality of people. And this is for treatment of COVID. And on this chart, you see the studies on the left in the column. And also you have something like risk ratio, which is like effect size measure for statistical tests. And you will see that some studies report that it's beneficial to adding corticosteroids to a hospital care. And for some of the studies, it's not like really, we are not really certain about the outcome. So what we're trying to do in the systematic review, we try to collect all of the available studies in an unbiased way, and then estimate the final effect. And the deltoid you can see on the bottom on the risk ratio here is sort of like our final decision about whether it helps or not. So we see that it helps a bit in terms of mortality. So what I want you to remember is just systematic review is a set of studies. So we try to, before I go into machine learning details, first I will explain the business process of systematic review, how it's being created. And first of all, people need to define the question, what they want to answer. And then they search for studies. And very strong requirement for the systematic review is that the search needs to be very comprehensive, meaning that looking only for one database is not enough. We need multiple of databases and we need to be very, very sensitive in our search. And then since we have multiple databases, we end up with a lot of duplicates. And then we need to remove these duplicates. And then since we have some collection of studies, then we need to select these studies. And in the process of selecting the studies, we have two sub-stages, which is we look only as on the title and abstract or on the full text. And basically, with title and abstract, we need to take into account that we don't have access to the full information, because this is only what the authors reported, maybe the journals reported. So we need to take that into account, that maybe the outcome, as I shown on the previous chart, previous slide, the all-cause mortality may not be mentioned in the title and abstract, so it might not be a good reason to exclude this study from our systematic reviews. And then when we finish selecting the studies, then we're doing extraction, and from the extraction, we end up with analysis. And analysis is basically this forest plot I shown you on the previous slide, which is some sort of a chart that aggregates all of the studies. So this is what this is systematic review. And now since we have a systematic review and we want to help in screening process of the systematic reviews, what we do, we look for benchmarks. And we found some data set called Cohen's datasets. And basically it was defined in such a way that we have a list of studies written in language, in like natural language. And then we have decisions from the reviewers, which is like 1 or 0. So whether we should include the study for the process I've shown you. So whether we should go for the full text and then doing extraction, etc., or we should stop looking at this particular study. So this is a binary classification problem you can think of, but we have a different goal for systematic reviews, because the main goal is to be very comprehensive. So we want to avoid, we don't want to miss studies. So our goal, in other words, is to maximize recall or sensitivity. So for such classification problem, we could use different metrics, which is well known, like F1 or average precisions. But these metrics are very generic and they don't focus strictly on maximizing the recall. They just find you some balance with some like geometric average, for example, F1, and average precision is like the average area under curve of the precision recall curve. So these metrics are fine, but too generic for our purpose. So in this data set we found for the benchmark, we found that there are 16 systematic reviews. And just remember that one systematic review is a list of studies with binary decisions 1 or 0. And we have different numbers of included studies in these reviews, from 9 to 150. And imbalance ratio we are discussing here is roughly 4%. So the authors of this dataset defined the task. So they split the dataset on 50%, and they train on this 50% of data in the cross-validation fashion. And then 50% of studies go for like real-world testing, verification of the model or algorithm. And we do that for each fault in the cross-validation training, we just make a prediction, and then we average prediction that goes for testing. So this is the data set we have for the benchmark. And for the benchmark, as I said, F1 or average precisions are not a good metrics. Like they're good metrics, but not very good for our purpose. That's why we need a different metrics. And another group defined a metric called worked safe oversampling, WSS. And it looks like follows. It's basically the trade-off between recall and work. So if we want this to be high, we want the recall, so sensitivity we want to be high, but at the same time we want the amount of real work, which is, so real work is basically all true positives and all false positives that were returned by the model. The person needs to look at these numbers. And then it needs to, this is like, if we divide that by number of all of the documents, then we end up with the work we have to do for the systematic reviews. So we want WSS to be very high, but some groups define that we want WSS for recall defined upfront. They define like 95% of recall. So we are sure that we didn't miss any studies. And it's not like 0-1 metric, it's basically from different ranges, it varies. So sometimes 80% is good, sometimes 70% is good, sometimes 90% is very good. So it depends on the data set. And another property is that if we have a dummy model which predicts every row as 1, then WSS will be equal to 0, because if we predict everything as 1, then we for sure don't miss anything, because we have recall equals 100%, but we also need to look at every single row. That's why it's equals to 0. And I used to say that it's hackable, because it relates to a number of examples. So if we have 1,000 examples in a systematic reviews to screen, then we have some sort of WSS value, but we might have like 100,000. And then we can have like artificial very high number of value of WSS, because it depends on the N. And also, as I said, we cannot compare between data sets, because since it depends on the N, then like 60% or 30% on one data set may be a good score we get from the data set, from the model. And another interpretation of this of this metric is that it works gains over uniformly distributed positive examples in the data set. So if you look at the equation, recall basically is defined as work plus worked saved over sampling. And if you try to see it on the chart, and on the y-axis we see recall, and the x-axis we have number of documents, you can see that if you have documents distributed in the sort of like uniform fashion. So let's assume for the example that we have 100 studies and 10 included like positive examples in our data set. Then if are like uniformly distributed, so a positive example is every 10th of our data sample in a data set, then if we screen 10 examples, we end up with one positive example. In other words, if we do 10 examples, which is 10% of our work, we will get one positive example, which is also 10% of our recall. That's why this dotted line as a diagonal on the chart is sort of for this uniform distribution of positive examples in data sets. And what we are measuring is WSS, and we would like WSS to be measured like a gain we get from like ranking documents in different order. That's why, yeah. So this is another interpretation for that WSS, and we'll use that metric later to see the score of our models. So since we know the benchmark and we know since we know the benchmark, the data set, and we have the metric defined, now it's time to train some models. And we tried 3 different models. So first of all, we tried some techniques from convolutional neural networks with 1D filters and glove embeddings. You can imagine that if you have a text and you tokenize the text to be a list of words, and then each word you sort of map to some embeddings, which is like a vector. In this case, we use the glove embeddings. Then you end up with like a matrix, because each word is mapped to a vector and have lists of lists. And since it's like a matrix, you can think of this matrix as an image. And since it's an image, you can apply some techniques from image recognition, like convolutional neural networks, to retrieve some higher level embeddings of this of our text. And then you're just adding some aggregation technique. In our case, it was mean, and then you have a linear layer to classify things. Another model we used are LSTMs, and LSTMs are they add some sort of like time dependency between words. So in convolutional neural networks, you have like only local, depends on the size of convolutional, you have like local relationships between words. Here you can have like much longer relationships between words, and you can have one direction relationships or 2 directions relationships. And we tried some extensions of LSTMs for text. So we used variational dropout, which has some Bayesian interpretation of a dropout, but for the practical purpose is that the dropout mask is sampled only once. for each sample and not for each sample for each like time step. So that's why we can estimate it better. I mean, like theoretical explanation of partial dropout are like much more complex to be put in the presentation, but this is like practical tip to use. And also, if you have regular like dropout, you can extend that because to be like drop connect. And the idea is that instead of masking only the output activation of the neurons, we can actually mask the whole matrix. And in this case, we had like one sampled matrix for a drop connect mask, only for the time dependency matrix that you have in LSTMs. That's why it's recurrent dropout. So it gives you much higher regularization for LSTMs than the regular one. And also embedding dropout, which is basically if we have the words and we have like some preliminary embeddings from ILMO, then we actually, it's equivalent to masking the word for the dropout. So we kind of hide the words and try to still predict to classify examples by not looking at specific words because they are masked with dropout. And the last model, which is the most famous one recently, is BERT. In this case, it's a variant called BioBERT. And BioBERT work is a language model, and that was trained using something called self-attention blocks. But it was trained to predict the masking words for the sentence and also predicting the next sentence prediction. So whether two sentences in the text were followed one after another. So they trained the language model from a very, very large data sets and obtained some embeddings for the words. What is important here, the BERT's embeddings are like contextualized. So it depends on the embedding of the word depends on the context they are put in. So I reference to some related papers for these techniques I mentioned. So we trained the model. Our score was WSS, but since our goal is to have very high recall, we defined WSS for 95% of recall. So we end up with the following results. And as you can see, these deep learning techniques, which is, as I described, CNN with Glow, LSTM, or BioBERT, are inferior to a solution of Swift review, which is some tool for screening for systematic reviews. And in the paper, they explained that they use SVM, TF-IDF, and LDA, which is like latent Dirichlet allocation, which is like a technique to assign topics vectors to a text. So we can think of like a method to extract features from text as well. And they are like very good for that. So we tried to investigate our problem. So we need to ask the question why it works so poorly. So we found some paper called DocBERT, and they actually compared BERT with different techniques for different data sets. And you can see that there exist actually papers, the data sets, which are not very hard to model. And for example, SVM over TF-IDF in TF-IDF is very competitive to the recent state of art, which is BERT, for Reuters dataset, for example, in this case. But actually the answer was slightly different because, as I said, we want recall to be 95%. And one of the systematic review from this dataset had only 8 examples, positive examples in the test set. So if you have 8 positive examples, then your resolution for recall is like 12.5%. So you can have 100% or 87.5% of recall. But if we want 95%, then we need to decide whether we want to take this number, which is like 20% of WSS, or we want this 70, I know, 273 maybe percent of recall. So the difference was that the authors of the paper said WSS at 95% of recall and they took the higher value and we took the lower value, because the lower value, which is 20%, is in the absolute distance, it's much closer to 95%. So if we see the real result on that, it seems that because we reproduced the paper and took a different value, is actually different. And actually, in this case, if you do a thorough investigation, you will see that the methods are working well. With BioBERT, we have very weak results. I don't know what was the reason. I didn't investigate it further, but we were using some library, and I know it was under active development back then. So so maybe there was some bug or something. I don't really know. Maybe that's the case. Maybe the task is very simple itself, because we know that for screening people use mostly keywords, and BioBERT has some contextualized embeddings. That's why it may work poorly for the out of distribution data. It's still a good question to answer. So we trained big models for some text, like some data sets which are not very large. And some people think that you cannot train big models for like very small data sets. But actually, it actually makes sense if your data set doesn't require this complex modeling. But in theory, you can do that. And it's not true that you overfit always with big models to small data sets. It matters how you regularize the model, and also what you can find from some papers, that it matters how you actually train the model. So, for example, in the paper from Jeremy Howard on the universal language model fine-tuning for text classification, he mentioned some sort of fine-tuning techniques, which is how you should control the learning rate, or how you should freeze your layers in order to get the best results. So the idea is that you don't train the model just plainly fitting. You just have some strategy for your learning rate. That's why we call it like learning rate schedulers. And also, since there's like a very big hype for BERT, actually BERT is not always superior. Maybe sometimes is, but its different methods are very competitive. So if you look at the chart that I presented previously, different methods like LSTMs also are very competitive to BERT for some applications. Also, there's a different paper that if you train convolutional neural networks on a very big corpus and you have some special architecture, still it can be competitive to BERT. And also, there's also a nice paper that mentions how BERT poorly understands the numbers. And it seems like the GLOVES embedding itself, if we look at the distances to words, from words to words, and from numbers to numbers, actually it understands it's the best, the GLOVE embeddings. I recommend to look for the papers I referenced. So I said that if you look at BERT here, the score, for example, for the Reuters dataset, and you take a look for the LSTMs with the technique called knowledge distillation, and knowledge distillation is a technique that you take the knowledge from BERT and you use that as a regularization for LSTM. So you just measuring the distance in distribution between, so you have like two teachers in this. You don't only have the expert, but you also using the different model to regularize. So we have like two teachers in this process. And when I speak about training large models, as I mentioned, you can train big models for quite small data set. It's fine. You can train it well if you have some learning rate schedulers. But if you don't have a big validation set, then you have some problem to actually improve over your hypothesis. And I recommend not to experiment extensively. And actually, there's like a paper, very nice one from Andrew NG, that he shows how you can actually overfit to a validation set, even in the cross-validation fashion, and how you should pick your hypothesis and correlate it to hypothesis. And also, if you don't have big validation data set, I don't recommend to use error stopping, because error stopping is a technique that the idea for error stopping is that we should stop training as soon as possible, so we don't overfit and we monitor the validation score. But if you have very small validation data set, then you can easily end up with some peak of the validation set. And then actually in the test set, it will work much worse. So you have different techniques if you want to train for like longer time on the training set, and you can do that with the learning rate schedulers I mentioned. And also, early stopping confuses if you do that in a cross-validation fashion, because you split the data sets in different folds, and then if any fold has different early stopping, then you don't need how to retrain it again. And also for language models, you can have different hyperparameters, and we try to tune them on the small validation set, and it really helped. We used a framework called Optuna, which introduces some Bayesian optimization for the hyperparameter space. And basically, the gain was not significant. I will show you later one chart from Optuna, and you might decide for yourself, is it worth or not. So my advice is to spend more time on business understanding of the process. And also, if you have very big models and very small data sets, you want to track your metrics more frequently, because you rarely need to go through your whole data sets to actually see the improvement. Usually, if you have the good language models, which are pre-trained on the big corpus, you will need a few examples, because from the GPT-3 paper, you may know that like language models are few-shot learners, so they need a few examples to learn something. And yeah, and I recommend to have like monitoring not every epoch when you sweep the whole data set, but much more frequently. And you could say that you could lower the learning rate, but it's also tricky, because if your learning rate is too little, then you cannot actually train very efficiently. And also, especially for the BERT models, I recommend to use don't experiment with the batch size, that use the batch size that so it fits your memory of GPU to be maximized, so you don't lose any resources in the training process. And also, BERT is designed in the basic form that if you want to have batch size equals to 4, you need to 12 GPUs, gigabytes of GPUs. So we bought a GPU like 11 gigabytes, and we need just 1 gigabyte to have one additional batch size for training. So by 12 gigabytes of GPU. And also, if you want to have regularization technique for BERT, because in BERT you have something called normalization layer, you need to kind of exclude these layers from the weight decays, because it will mess your gradient propagation in the network. So I'm using some regex to exclude these kind of layers from BERT. Okay, so that was the settings we had, and now I will try to explain some paper that was also very beneficial in learning. And this is something called focal loss, and it's especially designed for the imbalanced data set. And what it does, it kind of flattens the log loss you have for the classification. So you can imagine that if you have a positive example equals to 1 or 0, like a negative one, and then you want to optimize with your optimizer, you want to learn the model, then if you accomplish some sort of level of confidence, like 0.6 or 0.7, actually you stop training. Your loss will be equals to 0, like mostly 0. So basically, it will do two things for you. First of all, if you see a very easy example that you already know, then it stops learning from them. So it prevents overfitting, and also it allows you to train longer. So if you have a very few positive examples, then you can like sweep multiples of times through your data set and actually don't learn from this easy examples that are our like class, which is just like we have a lot of examples from like because we have imbalanced data set. That's why we have a lot of zeros in the data set. So you can actually train longer and more frequently see these actually hard examples, which are the positive examples in our data set. So we can normalize your log loss with this kind of flattening term here, and it works very nice. Another trick you can do, also from that paper, is that if you have a prior knowledge about your distribution of labels, output labels, and you know that your imbalance ratio is like 99%, for example, then you can actually input that knowledge into your network, into your neural network. So you can add the bias term as on the screen, and the argument for log is like inverse odds ratio from logistic regressions. But the point is that this p-value, you can think of that as probability that if you have a dummy model, then the probability that the model will return if you have a dummy model for the negative class or positive one, depends how we interpret that. So if you have like 1% of positive classes, we can put that 1% here and then have this kind of prior knowledge from human to the neural network. So this is a very cool technique that I recommend to use. So far we had a lot of like 10 examples, 15. I've shown you on the slides earlier what's our distribution of our data set, and we had from 9 to 150 examples. But and you can train that. You had some problems with validation, of course. But we once had a client who had only 3 positive examples for his systematic review. And with supervised method, that's not much we can do with 3 examples, because we don't even know how to split that, how to test that, and how to iterate over the hypothesis we have. So we try to go with unsupervised models. And perhaps some of you know that BERT model, which is like very famous in the unsupervised way. So if you take the embeddings from BERT and you try to use them just as they were returned from the model, you actually don't get good results because it wasn't trained that way. So what you need to do is actually need to train that in a different fashion. So we used a triplet loss, which is some sort of idea that for your study, you would like this study to be close to all of the positive examples in your data set, but at the same time, you would like them to be far away from the negative examples in the data set. So utilizing our label as an information, how close the data points in a space should be together or far away. And you can do that introducing such laws. This plus is like maximum of 0 and argument here. M is some sort of margin, which is we can input a priori how far you would like them to be. And DAP and DAN are distances for the anchor positive and anchor negative examples that is returned by the model. So this is idea behind the triplet loss. So there are different losses as well, and there is also a nice paper from Kevin Musgrave about the different metric function. And they actually reported that triplet loss is still a good benchmark, and they did a very thorough validation of the different losses, and it seems that the relative improvement over triplet loss in reality was not that high, and also for contrastive loss, which is a different loss for unsupervised learning. Because people in these papers reported some gains, but these gains were from different architecture decisions. For example, they choose a different architecture, or they choose different hyperparameters, and that's why they accomplish a good score. So triplet loss, what I'm trying to say is that triplet loss is fine. You can use that, you can try different metrics, but probably it's not a good use of your resources. We had a data set which was collected internally. We managed to collect 36 systematic reviews with the statistics as follows. And we see that in the included ratio is 2%, but we have from 2 to 250 included examples in the reviews. So we end up over these 36 systematic reviews with roughly 2,000 included examples. So still not a lot of examples, but if we go into unsupervised learning with triplet loss, we actually need to generate triplets because we need this positive, anchor, and negative example to be once in a data set for training. So from that, we actually can generate 85,000 examples for training, which is a significant number because now we actually can validate the model properly and be sure about the score it gets. And what is important here that in the triplet loss training, you you basically don't want easy examples. You want actually the examples that you would distribute in the space somehow. So you have some hard mining techniques in this triplet loss paper, which is how you should select studies for your optimization. Here, we didn't do that because we know that our samples in one systematic reviews actually are semi-hard by definition because they come from some search strategy which represents some specific domain. So these studies in the paper are quite similar, but we need to know the similarity anyway. And we measure the area under curve for the ROC curve, which is sort of measures the separability between the classes. In our case, we have the positive examples and negative examples, and we treat the distance as the prediction and the label as the label. That's why we can use that metric. So about the hyperparameters of this triplet loss training, first of all, different papers report the importance of the batch size. You can try that. We didn't verify batch size for the reasons I mentioned, but some papers report that if you increase like significantly the batch size, you can get very, very good improvement of your model. And also what's important here is that you need to project your embeddings, because by default BERT returns like 768, I think, and you need to project that to lower dimensionality, because otherwise you will have some problems with setting up the distance thresholds to actually make a prediction from that. So if you train such model, what is most important? And of course, learning rate is very important, but also the triplet distance, which basically means whether we use, because I never told you what distance we have been using for that model, and you can use either cosine distance or L2 distance, and actually it matters very much whether you use L2 or cosine distance, and also triplet margin, which is like you need to tune that a bit, how far you want the data points in the space to be distributed, and poolings means that you may use the CLS token from BERT, or you can use the mean over all of your embeddings, and different like less related hyperparameters. But anyhow, if you take a look at the optimization history of using Optuna, the results are not very, like the gain we had are not very significant. We quickly got improvements to 86%, and then we managed to improve like 1% with 40 trials, which took us, I don't know, perhaps 2 weeks of training. So since it was doing automatically, it was fine, but I don't recommend to spend a lot of time on that. So since we had our embeddings, so for each study in the systematic reviews, we have embeddings, we can now try to evaluate them. And what we can do on our test set is actually, we can do some sort of naive evaluation. So what I mean by naive evaluation? So what we can do is we can transform our studies to some embeddings like a vector, feature vector, and then we can pick one included studies in the review and try to measure distances with respect to this one specific studies. And then we can repeat the process. We can choose the different study and then rank the documents on the list as well. We can choose a different one and then rank the documents as well. And here we can see, if you take a look at the ranking, how much recall we get. And this is like one system, and we should end the process when the recall is equals to 95%. And you can see from that, this is a nice review, and we actually won here. And this green PsyBERT, which is another variant of BERT, as I told you, it doesn't work in unsupervised fashion, and basically it's like a random order. But we know from that TF-IDF is also a very good benchmark. Here, for that example, we clearly had some problems with, I don't know, maybe distribution of data or training itself, but the blue line is like very poor, and this is our model. But also this is interesting example, since TF-IDF itself is a very good benchmark, and it ends up the race to achieve 95% very quickly. Actually, if we take a look at the higher requirement, which is like recall 100%, we actually end up in the same way. So our blue line and the red line end up in similar point of number of screen studies. And for example, Spectre, which is some different idea that they build embeddings, but over the citation network. So if they have one study and one study cite another study, they think that they're close in other, but if they are like far away in the citation network, they actually should be far away in the distance, in the metric space. So the distances should be higher. This is like another idea of the Spectre. So we tried to use that method and to also evaluate WSS, and we see that actually TF-IDF for the test set is very strong benchmark. For the validation set, we are better. But if we take a look at the WSS at recall 100%, then actually we won, but maybe we just picked some recall value that it works well. Anyway, what I'm trying to say, you can do that, but TF-IDF is, which is very simple, still for our purpose, our challenge is still a very good benchmark. Yeah. So these were two approaches, and until now, I set up some training setting, which is in the first case, we needed to label 50% of data to start training, and then we need another 50% to evaluate the model. That was the first case. The second case, if you had like very little include positive examples in the data set, then we actually needed at least one included study to start ranking, so that was some drawbacks of the approaches we had. But still, regardless of that, we can use them in different applications. So first example with supervised fashion is that we can update an existing systematic review, because there exists some systematic review in the world, and we try to update to look for some additional literature that they should include in the studies. And also we can do that for validation. So if we have some decision for screening and some data sample or some record were rejected for some reason, we can still validate that. Was it a good decision or bad? So we can do that in the sort of like cross-fold fashion. So we can take the whole data set, train the model on the fault, and predict for a different fault, and etc. And in this kind of fault training, cross-validation with faults and prediction for each fault, we can actually get the verification of the existing systematic reviews. Another problem we have that I kind of didn't explain you that is that we only rank the documents with the classification, but we actually never told you when you should stop. We never told you that, okay, you should stop screening now because you achieved 95%. We do that like afterwards, like a posteriori, not before that. So basically they're useless in terms of saving the real work, and this is a huge drawback of the benchmark that was created here. So we need sort of to map the scores into some labels to actually say this is 1, this is 0, and then you actually should look at that and shouldn't look at that row. So if you want to convert that into binary labels, it's not so easy if you have the very little validation set, because we try to estimate these thresholds for the imbalanced data set with different ways on validation, on training sets, and different techniques. But in any case, we sort of observed some problems that the results on the test set wasn't as expected. It wasn't bad itself, but it wasn't like we expected. So if we expected like 90%, sometimes we had 80%. I mean, vice versa. We had like 80%, we expected 80%, and we got 90%. So it's not very easy for the imbalanced data set to set up the threshold. You can do some argmax, but so the thresholds would be like 0.5, but it doesn't get you to the required recall. So it's not for our case. You can try different methods, like try to embed that threshold estimation like itself in a training procedure, which is if you have like shallow models with only one layer of features. You can use SVMs, which will give you 1 zeros out of the box. For deep models, you can use something called sparse max. We also experimented, but they don't get you required recall anyway. For unsupervised model, it's not also trivial because KNN, which is nearest neighbors, also doesn't work well for imbalanced data set because you have some distribution, and in most cases you will end up with bad labeling here. So we don't recommend to use KNN here as well. So regardless of the problems we had with estimation the thresholds which impacts the robustness, I will show you some case studies. So this is the part that I will explain how we actually helped in COVID. So we are asked to help in screening for the physical distances and wearing the first face masks to prevent from transmission of COVID. And they had around 20K documents to screen in 2 weeks. And now they have like 60 documents for update. And they had like 40 people. And the idea here is that they had like 40 people with different experience. So they could do the work, but we actually could verify the model with the setting I told you. So we could like split the data set into the half, like 50-50, train the model here and apply on the second half. And then we can switch and do the same. And because it was a double screening, so 2 people were assigned to one study, they actually were cases when 2 or not very experienced people actually missed a study that model managed to detect as important one. So we sort of identified the missed evidences from people. And this was the work that was cited more than 1,500 times. And actually, after the publication, the WHO changed the guidance of wearing the masks. And also the second case we had is about the update for anticoagulation for thermal prophylaxis, whatever it means. I don't really know, with patients with COVID. And the idea here is that they have a lot of documents coming in every month. So this is the living systematic reviews, and we managed to like have the workload reduction from 80 to 95%, still having this 95% recall. But this actually is a case when I told you that this kind of WSS metric is sort of hackable, meaning that it depends on the number of studies you have, because they had a lot of studies. They had like 100,000 studies to screen the first updates and roughly 200,000 studies to screen the second update. So we could easily discard a lot of trash in the data set. That's why we have a very high work reduction. And most of the reduction was because they couldn't cope with the duplicates, and we helped that with our internal tool. And basically, we call it super duper, but the idea is that with the embeddings that I showed you earlier that we trained for each study, and then we had like a small label data set to estimate the threshold, and then we can actually remove the duplicates based on that. So cutting so detect some groups of documents that are similar to each other. And the duplication comes, as I told you in the process, that the idea of systematic review is to be comprehensive. So, so they end up with a lot of duplicate of the same study from different journals, some conferences, so maybe because sometimes also the paper evolves over time. So sometimes the author is added to a list of authors, the publication date changed, but basically it's the same study. And if you look at the text, actually you can detect that. And for some reason, current approaches, current market tools look at these metadata like authors, publication date, or etc. But we actually came to the conclusion that it doesn't matter, because if people do screening based on title and abstract, they don't need that. And if you take into account this additional metadata like authors, publication year, you end up with, you won't be able to resolve. It's like some conflicts you have. It's not a very easy task as well. So we just recommend to, first of all, don't remove, aggregate the metadata, because they will be useful later if you want to retrieve the full text. And you should focus only on title and abstract. because this is what you read, and based on what you should make a decision. It's like very simple improvement of business if you understand the process that we proposed. And also taking into account that you should deduplicate very thoroughly if you want to train the model, because otherwise you will have a data leakage, meaning that a study which is very similar, if you like have a split of studies into like validation, cross-validation, or test set, you will think that your model performed well, but it won't in the real world because you have a data leakage in your training process. So this is like very important step for training as well. And it's like n square complexity to do that, because for each study you need to look for the list of all other studies to compare with. And people use some heuristic and try to sort the numbers, etc. So yeah, so it's very important task, but people don't discuss it very often in this domain. And from our experience on this hematology review case study I showed you, we actually managed to save like 50% of work just removing duplicates. And it's like much more than the different market tools that we compared with, that they actually used also the metadata. Yeah, so I don't have much time left, so I will skip some slides, I think, because now I have some very nice trick how you can optimize this duplication not to be time square complexity. So if their slides will be accessible, you can take a look at the math here and the reference paper. But basically, what I try to tell you from the previous experiences, that first of all, we had to train models for each systematic review, and it wasn't very well, because for deep learning models, it's not so easy. For small models, you have some variability in training related to randomness, to different hyperparameters. So this is what we don't want to have in the final approach. But also we would like to work with these highly imbalanced systematic reviews, which are the cases that I mentioned, that we had a client with 3 included studies only. And you should work with that as well, which is not possible with the current approaches. The second thing is that we would also like to save real screening work, but I mean estimate the validation, the threshold for the test set very robustly. So we actually know what to expect from the model, and if you have imbalanced data set, we can do that robustly because it's imbalanced. Even if you try to look for some statistical methods like bootstrap, etc., it's still not very valuable in this case. So this is our goal. And also what we said, we had only 2 applications. First of all, we want to update the model, or we can have verified update the systematic review, or verify the current existing systematic review. So in the supervised fashion, we needed some training data to even start training, but we also want to help with creating systematic review from scratch. There are some studies that try to use active learning approach, so they retrain the model every time the decision is made, and still a good way to go. We'll try a different solution here. And also, if you discuss with some people in the industry, they actually do screening in a different fashion. They actually don't follow the predictions from the model. If you even do some ranking, or even do some binary classification, you still end up with people wanting to explore the literature, not to follow the ideas. So for example, they want to check one criteria, whether, for example, it relates to randomized control studies. And if it does, then they want to select based on that. So it's sort of iterative. Or they want to exclude studies that refer to human and not to animal, for example. And they just want to have a group of these studies and reject the studies in the screening process. So to get our goal, to achieve our goal, we actually need to go do a step back and understand the process. So we do all our research, but we actually need to take a look at the process again. And before selecting the studies, we actually have 2 steps, and these are search for studies and something called eligibility criteria. And search of studies basically are expressed, search of studies is done in databases, but the databases allows you to type the queries, but using Boolean logic. So because of the Boolean logic and Boolean expressions, they actually end up with very inaccurate results. So they have like a lot of trash in that data set, which is like the output from the Boolean search. So this is like a drawback. And also we can see that if you have the whole problem compressed into the binary classification, we actually don't allow people to change decision very easily. And we had this case that, for example, one group decided to exclude some studies, like some very low evidence studies, after they realized that different studies are available on the market. So for them, it's sort of like prediction what's in the database. So they define this eligibility criteria. So they predict what's in the database and what's not in the database. And as any machine learning application is basically some sort of every machine learning problem is to decode the signal. So if you have some label from the expert, you want to know what factors and what compositions of factors bring you to those particular decisions. And if you don't have a lot of data, it's very hard to later on work with that. You can train the model, but validation is a bit tricky. But if you look at the process, actually, people define what they want. So they know the factors and they know the compositions of them. So for example, for systematic reviews, people might define that I want randomized studies only, and I want the studies that refer to a population that describes some adults older than 60 years old with some stage of asthma. Or they want studies with 10 participants only, or studies that relate to particular drug, how long people actually had this drug. So this is actually, so we have this kind of criteria for people to use. And our challenge that was defined in this literature so far was as follows. We had a space of all documents, and then we found some space of matching documents that matches our criteria, and then we have some training signal only here that is sampled from the whole space of documents. And the problem is that if you have multiple of criteria and to try to combine that criteria into one final decision, which is 1 of 0, you may end up with this imbalancedness, because some random variables, but here I mean like some diseases, for example, are very rare in the world. So if the one factor in this chain rule is like very low, then the whole decision will be like very imbalanced, like the label. So this is something you cannot work with having these approaches, and that's why you end up with like 3 included studies only that I described. And also it depends how you sample this data set, because we had once a case that the training signal itself, we had 20 data points, which is still imbalanced, but these 20 data points like were very close to each other. So they were speaking about the same. And what you need to take into account that all machine learning models actually interpolate, not extrapolate. So it doesn't behave well into the areas that we have no data. And if we sample in such a way that we have like many data points, but still very close in the space, then we cannot extrapolate from that very well. So this is where the lack of the robustness comes from, if we think about the problem as the binary classification. And also, I've told you this kind of charts with this kind of phrase to achieve 95%. Actually, you may remember that they looked at the beginning, they were very fast, but then it was like a very long tail to achieve this 95%. And one of the reasons for that is that people, because it's a challenge of prediction what's in the data, people define some indirect criteria. So the criteria that doesn't match our initial criteria, but we need them as a backup decision, sort of. So they include that anyway, but they are not like very close even to what we're looking for. So for example, people might define to go for adults, but if they don't have any studies on adults, maybe on children or vice versa. So they're not similar in the term, but this is what people define. So to solve that problem of imbalanced classification from like very sparse training signal, we actually came to the conclusion that we need extraction model that represents well inclusions criteria. And this is like an example from our like preliminary work. That if this is like one particular systematic review. So if you look in this review only on the binary decision, and we will now want to build and validate the model on that, we have the imbalance ratio like 0.2%. We have 63 samples. Here it's not bad, but it's worse sometimes. But actually, if you decompose your signal into the pieces that you actually understand and know, which is I need to know study type. This is what I shown you, study type. I need to know the condition. So the population that was it was an input for the study, or intervention. So this is a drug that people have, or the comparator, which is a drug that I want to compare for the placebo group, for example. Then you actually have much more studies to actually build a model and to validate that robustly. So we are in the process to sort of redefine the problem of text classification to be actually the extraction model. And we tried briefly with Q&A approach for that, but it didn't work so well. So we now work with purely extraction model for the text. Okay, so I think that's it. So thank you very much for your attention. If you have any questions, please ask.